want to mention, I'll hand the exams back at the end of class. Exam keys and blank exams will be posted on D2L there. I recommend that when you get your exam back to look over it. If you're not sure what you missed or why you missed it, maybe look at the key. That way you can kind of learn what you were doing wrong. And then if there's still questions, please ask. But try to learn from your mistakes before you ask, I think is a better way to approach that. Okay, so there's a study group trying to be formed. If anyone is interested, here's a sign-up sheet. You just need to put your name and your email address and what days and times work best for you about, I don't know, 3/4 of the way down. Okay, so if you're interested, there's already at least one person interested, so I think we might need two more maybe. One more person, 2 more people maybe. So if you're interested, maybe during break or after class, you can sign this and get that going. Okay. All right, well today we're starting chapter 3. And chapter 3 is all about the derivative. So in 3.1, and I've sort of listed the topics here in the order we're going to cover them. If you'll notice, we don't cover chapter 3 in order. The application section, or sections rather, are saved for the end of chapter 3. But today we're going to look at hopefully 3.1, 2, and 3. Where 3.1 we look at how do we define the derivative at a point. In 3.2, how do we define the derivative function, and how do we graph derivatives? And in 3.3, we start to look at rules or shortcuts to compute derivatives. And then 3.4, 3.5 and are devoted to different derivative shortcuts for particular types of functions. So honestly, once we hit 3.3, the derivative rules come really quickly. And then they all build upon one another. So like if we learn the derivative of, how to take the derivative of a product and quotient in 3.4, then in 3.5, when we start looking at derivatives of trig functions, you automatically start seeing derivative of trig functions that are products and quotients. So they're not exclusive, they sort of just compound on one another as we go through. 3.7, another derivative rule for composition. 3.8, implicit differentiation, which is a derivative technique when we can't explicitly solve for y or f of x. Then we look at derivatives of logarithmic and exponential functions. 3.10 is the derivative of inverse trig functions. And then 3.6 and 3.11 are the applications to derivatives, or some of the applications to derivatives anyways. So that's the order we're going to cover that. If you refer back to the schedule, the end of the syllabus, you have a better sense of what we're going to be covering in class. So you hopefully can print the notes out if you need those. But again, everything but like these last two sections, we're constantly learning new derivative rules and techniques, and they all build upon one another. So you get a lot of information really quickly. I would recommend doing some sort of note card system, whatever has proven in the past to work for you to memorize a lot of facts in a short amount of time. And then when we move into chapter 4, we're going to discuss even more, I guess, mathematical applications of derivatives, like what can we do with a derivative. And more of a mathematical sense is pretty much what chapter 4 is about. Okay, so the idea of the derivative is nothing more. When we say derivative, we just mean slope of tangent line. So when I say what's the slope of the tangent line at this point, I can say what's the derivative at this point. So derivative is synonymous with slope of the tangent line, which we saw in chapter 2 with a few examples, was synonymous with the instantaneous rate of change. So our instantaneous rate of change, the slope of a tangent line, the derivative, it's all the same terminology. I mean, it's different terminology, but it's the same idea. So, although we don't see this here in section 3.2, we look at the idea that the slope along a curve, so we're given this parabola f of x, the slope of all tangent lines throughout that function will be different depending on where we're at. So that you could see the slope of the tangent line would change depending on where we're located on any given function. But in this section, we're focusing particularly if you were given this point on f of x, say that's a x value a, what's the slope of the tangent line at x equals to a on this given function? That's what we're looking at. Another way to think about the derivative or the slope of the tangent line is how steep is the given curve at a particular point. So it also measures how steep we are at one point. So if you'll recall, in the chapter 2, we started looking at average rates of change, or the slope of a secant line, which is just the slope of a line connecting 2 points. So we started off with this as our average rate of change. And the slope of the secant line were the same thing. We just defined that as a change in y over a change in x, as x goes from a to x. Okay, so we then took the limit in order to define the instantaneous rate of change. So once we apply a limit to the slope of a secant line, that gives us the slope of a tangent line. This is also the instantaneous rate of change. So we had a question like that on the exam where we had tables we had to fill out, and then the second part asked us to guess what we thought the instantaneous rate of change was going to be based upon the average rate of change. So hopefully that's nothing surprising. And then once we compute the slope of the tangent line at a particular point, then we can write the equation of the tangent line just by our point slope formula. You know, this is y minus y1 equals to the slope of the tangent line times x minus x1. So sometimes we're after just the derivative, sometimes we're after the equation of the tangent line. So this is the equation of the tangent line. All right, so do y'all have any questions on that? I guess hopefully it's not anything surprising. We have seen this process a few times. We're just making it a little bit more formal. Okay. So again, I'm just pointing out, when we're asked to compute the slope of the tangent line, this is the formula we're using, excuse me, to compute that. So if, for example, find the slope of the tangent line on the graph of x squared minus 5 at the point 3, 4, and then write the equation of the tangent line. I'm going to abbreviate equation of the tangent line. So the equation of any line, you know, we're looking at it like this. That's ultimately what we need to find, but specifically that's the equation of the tangent line. So we want to make sure that the slope we plug in is the slope of the tangent line. That way it's specifically corresponding to that. So really the bulk of the work is in finding what the slope of the tangent line, what the derivative is for the given function at the given point. So the first thing we need to find, we're given the point 3, 4, we have the y1 and the x1. We need to find the equation of the tangent line. So let's fill these in since we already know them. So x is 3, y is 4. And the slope of the tangent line was defined as the limit as x approaches a. What's a in this example? 3, yeah, it has to be an x value. So we're finding the slope on this function at that given x value. So x approaches 3. A is equal to 3. So the limit as x approaches 3 on the slope of the line, or f of x minus f of a all over x minus a. So the two things here, the f of x and f of 3, we're given those two things. We're given f of x is x squared minus 5, and f of 3 is equal to 4. Is everyone okay with that? We're just fitting that into the definition we had. So notice, I mean, it's worth pointing out that how we define the slope of a tangent line or the derivative at a point, it's just the way it's constructed. X is approaching a, but the denominator is x minus a. So the denominator is approaching 0. So this is where all of those simplification techniques come in to compute the actual limit if it does exist. But by definition, we look at that and we say, well, that limit is undefined, isn't it? Because the denominator is 0. We saw that was not necessarily the case. Some things factor out, whatever the case may be. So as it stands, whenever you find the slope of the tangent line, there's always going to be some work involved to simplify and compute that limit. So we've got x squared minus 9. Sorry, the limit as x approaches 3, x squared minus 9 over x minus 3. And please don't get sloppy with the limit stuff. I saw that a lot on the first exam. People were writing things like, the square root of 25, x to the 6th plus 3x squared, whatever this problem was, all over 9 minus 7x. So that was the function given to us, and a lot of people were just saying, well, this is equal to the square root of 25 x to the 6th over negative 7x. What's wrong with that? What's wrong with saying that?
It's missing the limit.
Yeah, you're missing the limit. This function is no way equal to this function. It's two completely different functions. The only way that they're equal is if you have the limit as x approaches infinity in front of this. Otherwise, it's not true. It's just like saying 5 equals 8. So you've got to be careful with your notation. I mean, I know in your head you knew what you meant, but when you're writing stuff out like that, it doesn't make any sense. So don't get sloppy with the notation. Yeah, it's tedious to carry the limit through, but that's just what we've got to do. All right, so the denominator's approaching 0, but hopefully that's something we'll recognize. If we factor the numerator, the problem in the denominator will go away. So we have the limit as x approaches 3. Top is x minus 3 times x plus 3, all over x minus 3. So this issue is gone. And what is our limit? As x approaches 3. Yeah, x approaches 3, our function is x plus 3, 3 plus 3 gives us 6. So that is the slope of the tangent line. In other words, if we looked at the graph of x squared minus 5 at the point 3, 4, the line touching that point has a slope of 6. Do y'all have any questions on that? In order to define the tangent line, the slope of the tangent line, which is just a line constructed at a single point, we need a limit in order to do that. So that's why we spent chapter 2 talking about limits. And then when we talk about the next concept important to calculus, it's also defined with a limit as well. So we haven't seen the last of limits. Maybe once we get into 3.3, most of the limit stuff in chapter 3 is gone, but we revisit limits in 4.7, and we'll revisit limits again in the beginnings of chapter 5. All right, once we've had the slope of the tangent line, we then have the equation of the tangent line. So there's our point slope formula with the slope of the tangent line. Please make sure when you plug in the slope of a tangent line that you're plugging in a number. A slope is always a number. Specifically when we get into the next section, often people want to put another function of x in for the slope of the tangent line, but the slope will always be a number. So I mean, that's the equation of our tangent line. If we wanted to write this as y equals, we could. And then we'll look at a graph just to kind of verify what we've done. We have minus 18 plus 4. Oops. So that's the equation of the tangent line. Does anyone have any questions on that example? Okay, let's look at what we actually computed there. X squared. All right, so here's the function. Here's the point we're finding the slope of the tangent line at. So we found the slope of the tangent line to be 6. In other words, if we're on this function, the steepness is 6. So right there at that point, up 6 units over 1 unit is how steep that is. And then we said that our tangent line was 6x minus 14. So that's the line we constructed that touches the graph at that single point. I mean, you have to get really close to see that it's not touching anywhere else. But that's what our work shows us visually. I don't know if I can fit that.
maybe.
So are there any questions? Okay, next example, similar thing. Slope of the tangent line, and write the equation of the tangent line for 4 over x squared at the point negative 1, 4. So I need to first find the slope of the tangent line. So what would the slope of the tangent line look like here for this function? I'll start. Limit as x approaches
Negative 1.
-1 on what function?
4 over x squared minus f of
Yeah, 4 over x squared, f of x, minus f of a,
which is 4.
which is 4, all over x, yeah, x minus a, x minus minus 1, which is x plus 1. That's f of x, and this is f of a. All right, so then, again, by definition, denominator 0 doesn't necessarily mean the limit doesn't exist. Complex fractions, what do we do to simplify that?
Reciprocal?
Yeah, of, the what?
Numerator.
Okay, so what will we multiply through by?
Four over x squared plus 4?
4 over x squared plus 4. So that wouldn't, if we multiply by 4 over x squared plus 4, the conjugate of the numerator, we're not going to get rid of the x squared in the bottom. In fact, that would give us an x to the 4th.
Square root of.
Square root. So then we would have the square root up top divided by x squared, and then 4 times the square root of x.
Would you just find the lowest common denominator and multiply it up with that?
Yeah, so it's just the same technique. When we have complex fractions, it's just find the lowest common denominator, because you're clearing those fractions. The other option is to say, well, what is 4 over x squared minus 4? But 4 is really 4x squared over x squared, right? So the other option is to add those things or subtract those things in the denominator. If 4 minus 4x squared all over x squared up top, all over x plus 1. So that's the other option, is just to add or subtract those two things. But then you still have a complex fraction, but at least we have a single thing in the numerator and a single thing in the denominator. This thing would come up here. The denominator would be 1. So that's what that would simplify to. But again, once you've added and configured this fraction into this fraction, you still have the issue of the x plus 1 in the denominator, that you have to factor the top again. So if you want to take that route where you just add those things and then try to simplify, there's nothing wrong with that. It is the more lengthy of the two processes. The easiest thing to do is just multiply the top and the bottom by the lowest common denominator in the numerator, because the numerator is the thing that we're trying to get rid of, the smaller fraction. Also, remember on these, the thing you're trying to get rid of is the x plus 1 in the denominator. You don't want to multiply the denominator out, because then you're going to lose that in the process of multiplication. So we will leave the denominator as it is, x plus 1 times x squared. What does the numerator turn into? Yeah. 4 minus 4x squared. So notice that's exactly where we were. Once we added those with the common denominator, and then we multiplied by the reciprocal, even though we just erased it, that's exactly what we had. So again, the issue is still lingering here as x plus 1. The only other choice now that we don't have complex fractions is to try to factor the numerator and see if things go away. So we have the limit as x approaches -1. We factor out a 4. Leaves us with 1 minus x squared over x plus 1 times x squared. Is that helpful? Yeah, because what do we know about 1 minus x squared? Anything?
You're gonna get a positive result.
Do what?
You'll get a positive result. So it's like adding to the same.
A positive result for,
Whenever you plug in x
It's a
squared.
perfect square.
depends. What if I plugged in a half?
You can take out a negative and it'll be x squared minus 1, and then that's just going to be x plus 1 and then x minus 1.
Right, yeah, it's just the difference of squares, right? That's 1 squared and that's x squared. So the difference of squares is 1 minus x times 1 plus x. If you want to factor a -1 out, you can do that as well. So here, the factor of x plus 1 and the factor of 1 plus x, so the same thing, they go away. You've got the limit now as x approaches -1 on 4 times 1 minus x all over x squared. So that is a limit we can compute. Do y'all have any questions on this? So many of you lost a lot of points on the exam when it came to limits like this. So if you're still shaky on this kind of stuff, you know, really what it amounts to is simplifying things algebraically. You might need to go over algebraic simplification of various types of functions. Because that's really all it is. We haven't done any calculus yet, right? It's all just been simplifying that quotient to get to this point. And then once we get to this point, it's still an algebraic thing. This function is continuous at -1, so we just plug -1 in. That's really not a calculus thing either. So as x approaches -1, what does this function approach? Yeah, so it's 4 times 1. This is minus. X is negative 1. All over negative 1 squared. So that's that, which gives us 8. That is the slope of the tangent line. So it's a little bit different of an interpretation than we were taking in chapter 2. In chapter 2, what we started off with, we just started off with this limit, 4 over x squared minus 4 over x plus 1. We just looked at that as a function in and of itself. And we said, well, this function here that we're dealing with is not defined when x is negative 1. But what happens is that factor goes away. We have a hole in negative 1, 8. But on this function that was generated by f of x minus f of a over x minus a, the original function 4 over x squared has no issues at negative 1. Is everyone aware of that? We're kind of shifting our interpretation. The function in front of the limit is a specific function. It's f of x minus f of a over x minus a. Although it's related to the original function, it's not the original function.
0.
Okay, so slope of the tangent line, equation of the tangent line is y minus y1, which is 4. Slope of our tangent line times x minus x1. Hopefully that's not the issue. Is everyone okay with this limit stuff? Are there any questions? So the 8x plus 12, that's the equation of the line that touches at negative 1, 4. The point negative 1, 4 on the function 4 over x squared. So let's look at that. Okay, so there's our function, there's 4 over x squared. We're interested in the equation of the line that touches at that point, which we said was 8x plus 12. Anyone have any questions? So really at this point, it's just all mathematical. You know, we do have a visual representation of what we're doing, but as far as like a physical representation, we have to sort of wait until we're describing a function like a position function, velocity, temperature, profit, whatever, before we actually have a physical interpretation of this line here giving us the instantaneous growth rate at an exact moment in time. All right. Well, so you try the function square root of x plus 3 at the point 1, 2. find the slope of the tangent line and the equation of the tangent line.
six. No, it's not here. X.
This is like y2 minus y1, x2 minus x1. You're saying x minus this x value, y minus this y value.
That's why I was.
No, that's exactly what I did, but I'm just confused. I think she's
This is gonna work out.
That's what I meant, that's not my. You cancel out plus, oh no, it's multiplication.
Yep. That's the slope of the tangent line, right?
Yeah, I just squared the whole thing.
Oh.
But I think it's because I took everything else was plus one. I tried to do x squared.
I don't think that's right, because it's just square this here. You're no longer doing this function, you're not doing this function. That's the one with one, that way you're not changing the function. So just the context. I'm better than Joe.
I guess
Utilizing the context.
It helps make it less messy. Because I still got on the bottom, I got this.
So if you square that, you're not, so you're changing, you want to think of what operations can take place, you don't change it. Once you operation you know, because that won't help us. What we're trying to get is the next line up
So when you do this part down here, this one is where the bubbles are. Yeah. So I couldn't figure out how did I have the canvas in here.
Right now I have someone else picking up my this is not what works.
All right, one thing I noticed, and I saw this on the exam too, you want to not do this anymore. If you have like a, whatever, any function, let's just do something simple like this. In order to simplify that, you cannot perform any other operations other than adding 0 or multiplying by 1. Because if you do anything else to a function, you're changing the function. So the only options I have to simplify functions, and we're not dealing with equations, right? If it were an equation, I could square one side and square the other side, that's fine, if I'm solving an equation. What these limits boil down to is simplifying an expression. So if we take this expression and we square it to get rid of that radical, then we're no longer dealing with the same thing, right? What you're dealing with now is the function squared, which isn't the function. So just please keep in mind that when you're simplifying expressions, you have two options. You can multiply through by a form of 1, or you can add a form of 0 in, right? Like if I were to add 9 minus 9 into a function, that doesn't change the function because I'm adding in 0. All right, so I know it's super tempting when you see square roots to just automatically default to squaring it, but when you do that, you change the value, you change the expression entirely. Okay, so the slope of the tangent line is the limit as x approaches 1. Function minus the y value, x over x minus the x value. We only looked at, we looked at factoring with specific cases, but as a general approach to functions like this that involve radicals, the only approach we had was to utilize the conjugate. So anytime you're using or finding the slope of a tangent line on a function that involves a root, just think that you're going to be utilizing conjugates. Just like when we look at functions that involve polynomials, it's just factoring and combining like terms. Functions that involve quotients always are going to involve the LCD to simplify. Functions with radicals always involve the conjugate. Okay, so we multiply the numerator and denominator. Again, we're not changing the value, we're just multiplying through by a specific form of 1. And so let's do this work down here, and then we'll go back up to what we're doing. again, the whole point of the conjugate was now that we've introduced the conjugate, the numerator is just a multiplication, which turns into a difference of squares. So that's how we get the squaring inside the function, so we can get rid of the radical without altering the function itself. Okay, so the denominator we're just going to leave alone. The issue is the factor of x minus 1. We don't want to disguise that through other operations. And so when we multiply these two things together, these two things are just the difference of squares, a squared minus b squared. So in other words, we have the square root of x plus 3 squared minus 2 squared. So up top we just get x plus 3 minus 4. Which we see is just x minus 1. So that's giving us our x, that's giving us our x minus 1 up top, so we can cancel it with the 1 on the bottom. So that and that are gone. So that's what it simplifies to. The original function we were working with is equivalent to that function there. Just simplify it. So we're computing the limit as x approaches 1 on the function 1 over the square root of x plus 3 plus 2. Function's continuous at x equals 1, so we just plug 1 directly in, and we get 1/4 for the slope of the tangent. Do y'all have any questions on that? So really, you shouldn't see any curveballs. Everything we saw in Chapter 2 as far as simplifying limits will be here as well. Okay, so there's slope of the tangent line, equation of the tangent line is 1/4 x plus 7/4. So that's the line. If we were to graph this, we're not going to graph it, but if we were to graph it, that's this line right here. Do y'all have any questions on that example? Yeah.
Do you have to carry over the limit as x approaches to the m tangent and the y, or the equation of the slope? Or the
You
y
mean,
equals
like,
1/4 x?
This limit over here?
Yeah, do you have to bring it over and say, like, limit as x approaches 1, y equals?
No.
Okay.
So the limit is specifically designated to give us the slope.
Okay,
Once we have that slope, then we're just plugging it into that formula.
okay.
Yeah.
For 7/4, do you want it in that form, or can we leave it as 1 3/4?
Yeah, typically those, it's an improper fraction, but those are preferred.
Cool.
Yeah. Most of the time in math classes, exact values are preferred. Yeah, so please don't write the decimal equivalents to this, point, what was it, 0.25x plus point whatever. Keep them exact or in fractional values. Hopefully fractions aren't scary at this point. All right, so we're going to kind of shift gears and look at an alternative formula. The formula will give us the same exact results, but the way it's presented, it looks different. And this alternate formula is more, what's the word? It's more advantageous when we look at the definition of the derivative, but it is telling us the same thing. So let's say we had some function, that's f of x. And I'm trying to find the derivative at this point, which we'll still keep as a. And this is going to be f of a. So instead of saying I'm somewhere over here that we, in the previous formula we called x, we just reconfigure what we call this other value. We'll call it a plus h instead of x. So the only difference in this formula that we're about to look at and the formula we just worked with is we started with this value of a, and then we moved to some x value that we called x. Here we're starting with a and some other value that we're calling a plus h. So that would give us this point, somewhere over here. But in order to find the slope of the tangent line at a, what has to happen to a plus h? Just like in chapter 2, that point has to get closer to this point. How do we make a plus h get closer to a?
2a plus h?
To what? To a plus h. Close.
Distance between.
That's the distance between. But all I want to do is make this point approach this, or this value approach this value. How do I do that?
Just have h approach 0.
Yeah, you just let h approach 0. So just think of h as some step size, or some distance away from a. So that's the only difference here in how we label that second point, a plus h, and in order to make this value approach this value, h has to approach 0. So that's the only difference in our formulas. Does that make sense to y'all? Is there any questions? So that's what we have defined here, our alternative definition. And again, previous definition said on the interval a to x. This says on the interval from a to a plus h. Oops, I highlighted the wrong thing. Here's the slope of the tangent line. We allow h to go to 0. And this should resemble, if you're familiar with the difference quotient, this should resemble the difference quotient more so than the previous formula did. If you don't remember the difference quotient, it's kind of a moot point, but this should look like the difference quotient. So that's pretty much the difference quotient. All right, our previous example, we used the formula number 1 to find the slope of the tangent line on x squared minus 5 at the point 3, 4. So let's just go ahead and do that again. We already have verified what the actual solution is, but let's work with this alternative formula and see if we can produce the same result. Okay, so we're going to compute the limit as h goes to 0 on f of a plus h. What is a in this example? 3. Do y'all agree with that? Yeah, because it says right here, at the point a comma f of a. So this is the point x comma f of x. We should clarify that this, when you see this a, just think of a is a fixed x value. If we say x, then x is here on this line, but once we say a, it's specifically here or specifically there. It's at a specific location. F of a plus h. So f evaluated at 3 plus h minus f of a all over h. So it might seem a little bit more clunky compared to the previous example. In the previous example, this first part in the numerator was just f of x. Now it's a function of h, because this limit affects h. We have to actually find this or compute this, f of a plus h. So in order to utilize this definition, you will always have to compute f of a plus h, because only the function will be given to you. We are given f of 3, however. So let's maybe off to the side compute f of 3 plus h. So what's f of 3 plus h for this example? 3. That f of 3 is 4, but we're not going to have a specific value for that, because more or less in this definition, the thing that's varying is that h.
Got 4 plus 6h plus 6r plus h squared.
Okay, let's see if that's right. So we're just plugging 3h into the function. Our function was, what was it, x squared minus 5? So yeah, our function takes the input, squares it, and then subtracts off 5. So we get 9 of h squared, and we have 6h. And then don't forget the minus 5. Combining like terms, rewriting, I guess, h squared plus 6h plus 4. Is everybody okay with that computation? Are there any questions? So h squared plus 6h plus 4. So this was h squared plus 6h plus 4 for f of 3 plus h, and that's minus 4 all over h. So even a lot of times with this alternative definition, a little bit more work is done up front to compute that composition, but typically the quotient that you end up with is a little bit easier to simplify. So like this quotient, you can see immediately what happens. The 4's cancel out, right? Both of these terms up top have an h that get divided by the h on the bottom. So just write it out. That's the limit as h goes to 0. The top is h squared plus 6h over h, and then both of these things are over h. Dividing the h in the denominator by both terms in the numerator by the h leaves us with h plus 6. As h goes to 0, this limit is 6. So you can verify that that is indeed the slope of the tangent line we got with the other formula on the first example we worked. So that was, I think, example same as our first example. Do you all have any questions?
That's the M tangent.
Right,
correct? Okay.
yeah, that's the slope of the tangent line.
Okay.
Feel okay? All right, we'll take a break. Just moving forward, though, we're going to compute the slope of the tangent line on 1 over 2x plus 1. What process do you think is involved in handling this? Factoring, conjugates, LCDs, which one of those? Maybe factoring. Typically with fractions involved, the formula is already a fraction itself, right? It's the limit on the change in y over a change in x. Then we're going to stick an additional fraction into the fractional formula. We're going to have complex fractions, so lowest common denominator is involved. Hopefully at this point that we've seen enough of these where you recognize, hey, if I start out with a function that has this kind of thing in it, this is the process to simplify it, right? If I start out with a radical, conjugates will be involved. If I start out with fractions, usually lowest common denominators are involved. If it has neither, then usually it's just a factoring problem. So those are really the only 3 scenarios that we've seen, and we'll continue to see those. Okay, so let's take a break, and then we'll continue this example. I'm gonna pass out the roll sheet. If y'all can try to like zigzag it so it gets to every group. Just sign or initial your name. Okay. So in this example, notice it tells us just to find the slope and the equation of the tangent line. We've now seen there's 2 different formulas that give us the same result. So for this one, let's use the alternative formula. Use the limit as h approaches 0 on f of a plus h minus f of a all over h. What's a in this example? 0. A is 0.
When do you know whether to use this form or the form you did earlier?
So when do you know whether to use this formula or the other one? Honestly, it's not going to specify. You have either or you can choose from.
Do both always work?
Yeah, both of them always will give you the same result. Honestly, I would use this one because as we practice this one, it gives us a better feel for the definition of a derivative, which we'll see after this. But this definition here, the alternative definition, is more in line with that of the derivative. So the slope of the tangent line, we have to compute the limit as h approaches 0 on f of 0 plus h minus f of 0 all over h. Just fitting those components into the definition. And then we look at what we're given, f of h. We know what f of h is. F of h is 1 over 2h plus 1 minus f of 0, which is our y value, given as 1. So same boat we were in with the 4 over x squared example. Two options you have here either involve the lowest common denominator to get rid of the smaller fraction up top, or we can add the two quantities together in the numerator and then simplify from there. Either one will work. So we're going to multiply the numerator and the denominator by 2h plus 1. So what does the top turn into once we distribute?
1 minus 2h minus 1.
Okay, good. 1 minus 2h minus 1. So don't forget to distribute the negative 1 times the 2h plus 1. So really what you have is like this. So up top, we just have a minus 2h. Over h times 2h plus 1. So we see the h's divide away. So we have the limit as h goes to 0 minus 2 over 2h plus 1 gives us what?
-2.
Negative 2. So that's the slope of our tangent line. Any questions on that? And the equation of the tangent line, we have y minus the y coordinate equals to the slope, negative 2, times x minus the x coordinate. Or in other words, it's y equals minus 2x plus 1. So let me just put this here. All right, so there's our function. The point we're constructing the tangent line at is here. We measure that slope to be negative 2, so negative 2x plus 1. All right. Any questions in this material? So in 3.2, we look at this idea. What we've been doing in 3.1 is we're given the function, and we say at this value a, compute the slope of the tangent line and or the equation of the tangent line at a. But if we wanted to know at all values of x along that curve, what would the slope of the tangent line be? It would be really tedious to do those computations one at a time for all x values, right? Like, what if we had this previous problem here, and it said find the slope of the tangent line at the point 0, 1, at the point something else, another point, and another point, and you have to construct those quotients and simplify those quotients for each and every individual point you want to measure or find the slope of the tangent line at. So, you know, ultimately it's fine for finding the slope at a particular point, but, you know, the slope varies from x value to x value, depending on what curve you're actually on. You know, here's specific numbers. So here the slope of the line is 32 at an x value of 2. At an x value of 3, it's 0. At an x value of 4.1, it's negative 35.2. So we want to come up with a more efficient way to determine the slope of the tangent line at all points on a given function. And the way we do that is here, given to us here in 3.2, where we start to look at the derivative as a function. So the derivative as a function, you see it's just a slight modification of that alternative formula we were just working with. Still the limit as h goes to 0, but instead of f of a plus h minus f of a, it's f of x plus h minus f of x. So just for comparison, from 3.1, we had that the slope of the tangent line we'll put that new notation here, was the limit as h goes to 0 and this just gives us a number. This just outputs a number. What this new function is when we replace a with x, remember a is a fixed x value, like 2 or negative 5 or 0. And here we'll just let it be x. So it's still this thing that's varying along the axis. That gives us a function of x. So this is f prime of x. This is a function of x. So previously what we were working with is something outputting a number. In 3.2, what we're working with is this formula outputting a function of x, like 5x plus 4 or negative x squared or something like that. So this is the definition of the derivative. It's one of the most fundamental definitions in calculus. And so this definition, provided that the limit exists and x is in the domain of the function, you know, you wouldn't expect to be able to find the slope of a tangent line at some value that's not on the function. If the derivative exists, if this limit exists, then we say the function f is differentiable at whatever x value. So when we say differentiable, we just mean the derivative exists. If I say this function is differentiable at x equal to 5, that means we can define the slope of a tangent line at x equal to 5. The way this notation is read, this is read as f prime of x. And f prime is the derivative, is the slope of the tangent line, is the instantaneous rate of change. And you know, the reason that it's a prime is because it's derived from or based off of the original function. So it still maintains the same function name. It's just a prime to indicate that it's the first derivative. Okay. So modification replacing a with x gives us an output of a function of x, which is the slope of the tangent line at all x locations on a function. So back to this example, x squared minus 5. This time it just says find the derivative. So it doesn't say find the slope of the tangent line on x squared minus 5 at the point 3, 4. It just says find the derivative. The derivative is defined as, or is f prime of x, which is defined as the limit as h goes to 0 of f of x plus h minus f of x all over h. So I see this often, and to avoid confusion, we are computing f evaluated at the quantity x plus h. We are not computing f evaluated at x plus h. This is not what we want to think about. I see people do that, so you've got to know those are two completely different things. It's f evaluated at x plus h. So in that definition, we're always going to have to find f of x plus h, just like in the prior definition, we always had to find f of a plus h. We're, of course, given f of x, and then we allow h to go to 0. So let me note that here. We have to find this, or compute this, and we have to be given a function. So let's compute what is f of x plus h for our given function. We sort of computed this earlier. So there's f of x plus h, because this f, our f of x the input squared minus 5. So we have x squared plus 2xh plus h squared minus 5. Then we'll compute the full numerator. The full numerator is f of x plus h minus f of x. So that's x squared plus 2xh plus h squared minus 5 for f of x plus h. And then we have to subtract off our function x squared minus 5. So be careful, in the definition, we're subtracting off that entire function. So you've got to make sure that that -1 is distributed to every single term in your function. Oops. So simplified that, we've got an x squared minus an x squared. We've got 2xh. We've got h squared. And then we've got a minus 5 plus 5. So we've got 2xh plus h squared. Anyone have any questions on that? So then f prime is the limit as h goes to 0 Our numerator we saw simplified to 2xh plus h squared all over h. So as h goes to 0, what is that limit? 2x. So just like we mentioned, this thing outputs a function of x. It's 2x.
So is that the slope of the tangent?
So is that the slope of the tangent line? It's the derivative. It's the slope of the tangent line is partially correct. This is the slope of the tangent line on x squared minus 5 for any value of x.
So our derivative is just 2x. So this is
Derivative is just 2x, yeah. So if we go down below here where it said, our first example in 3.1, we said, find the slope of the tangent line at the point 3,4. Does anybody remember what that was? It was 6, but the x value of the point was at 3, right? So I just plugged 3 into that for x. I get 6. And we'll see that down here. So, the idea is that now that we have a function that describes the slope at all points on that curve, in prior methods computing slope at the point 3,4, at the point -520, and at the point -2,1 would all require 3 separate computations. With the new computation, the derivative function, we can actually compute these slopes at these particular points very easily. So we don't have to keep constructing those quotients. So let's remind ourselves that the derivative at any x is defined as 2x. That is the slope of the tangent line at any point on the function x squared minus 5. So if we're asked what's the slope on x squared minus 5 at 3,4, then our computation is simply what is the derivative evaluated at 3. Well, the derivative is 2x, so this is just 2 times 3, which is 6. So there's the slope of the tangent line on x squared minus 5 at the point 3,4. What's the slope on x squared minus 5 at the point -520?
-10.
-10. So that's just f prime of -5, which is 2 times -5. How about the slope at -2, -1? -4. So now we've got a function, we can just plug x coordinates in to find the slope at any particular point. Does that make sense? Do y'all have any questions? Yeah.
So for the derivative, when you find it, so for like the exam, let's say like, do we have to show the work for this, or can we just use like the power?
So the question is on the exam, do we have to show this work to find the derivative? Because what we start to see is shortcut rules. We do have a shortcut rule for powers. And the answer is if the question on the exam says, excuse me, find the derivative using the definition of the derivative, then you have to use this. Because this is the definition of the derivative. The things we look at after this section are all shortcuts, so we don't have to keep computing this limit every time we want to find a derivative. And yes, there will be one question on the exam where you do have to compute the derivative using the definition. So even though this is tedious, and at some point it becomes it becomes something we don't utilize, it is something we need to know. Because notice here, the function is x squared minus 5. The power rule says that 2 just comes out front to multiply x to the first. So there's those shortcuts we do learn, but it's not until the next section, and we need to know both. Yeah, good question, thank you. Any other questions? So a couple more examples like this. Find the derivative of 1 over x squared. Again, this is a function that involves a quotient. Our definition involves a quotient. So lowest common denominator process is going to be involved here. So you've got to remember the definition. So the definition of f prime is the limit as h approaches 0 on f evaluated at x plus h minus f of x all over h. You might recognize this process as a pre-calculus thing where they said, find the difference quotient and simplify, right? So all of this stuff right here is exactly how you saw the difference quotient. And the whole idea of finding the difference quotient and simplifying it, it really didn't have a whole lot of context in prior math courses. It was just, well, this describes the slope between 2 points, so I simplify it, big deal, what happens? Well, nothing really happens with the simplified difference quotient until we take the limit as that h approaches 0, then you get the slope of a tangent line. So there really wasn't enough context in pre-calc to understand fully why we were doing that. Why do we find the difference quotient and simplify it? That's so we can find a derivative. So let's compute f of x plus h. What is f of x plus h? Right. So the function just takes the input 1 over the input squared. We're inputting in x plus h. So it's just 1 over x plus h squared. And honestly, since we're going to utilize the lowest common denominator here, I wouldn't worry about foiling that out or expanding that. I would just leave it as x plus h squared. What's the lowest common denominator? Maybe that's difficult, so let's just ask the question, what's a common denominator?
X squared.
But this one's not x squared either.
X squared, x plus h squared.
Yeah. It's just the denominators multiply by one another. I'm gonna erase this, but just to show you, if you have 1 over x cubed minus 1 plus 1 over x squared plus 2 minus 1 over x squared, it might be tedious to figure out because we could factor this, can't factor that, x squared. It might be really tedious to figure out what's the lowest common denominator. So I would just recommend finding a common denominator. It doesn't have to be the lowest. The only advantage the lowest common denominator has over any other common denominator is that when you utilize the lowest common denominator, you just don't have to simplify when you're done. If you utilize just a common denominator, you'll have to simplify, but you'll end up with the same result. And I think a lot of times it's easier just to find a common denominator, not the lowest common denominator. So in that case, any common denominator can be found. Just take all three denominators and multiply them together. That will always give you a common denominator. So there's no thought required. We just multiply all the denominators together. We'd probably end up simplifying, but it's easier to simplify than to rack your brain trying to figure out, well, what's the lowest thing that goes into all three of those? I mean, most of the time it's straightforward, but just to kind of avoid that. So we're going to multiply the top and the bottom by that quantity. Leave the denominator, I guess, factored. What does the numerator turn into? What's x squared times x plus h squared divided by x plus h squared? It's x squared minus our second term, x plus h quantity squared. So now we have no more fractions within fractions. Remember, the issue with the definition is that h is going to 0. We have to somehow get a factor of h in the numerator to cancel with that factor of h in the denominator. So we're not done. Although this has helped us a little bit, we still have to expand x plus h, add, multiply by -1, and then add x squared to all of that. Let's just do that here. This is negative x squared plus 2xh plus h squared. When we expand this, and so we have this x squared minus this x squared, those are gone. We've got a minus 2xh, and we've got a minus h squared all over h. So same scenario we've seen time and time again with these. As h goes to 0, what's our limit? Is what? Negative 2x, right? So there's the derivative. In other words, that function, negative 2x, gives us the slope at any point on the function 1 over x squared.
What happened to your denominator?
That h divided this h and this h.
No. What?
Yeah.
Yeah, like
Oh.
world?
Yeah, what happened to all of that? We totally dropped all of that. Wow, huge oversight. That's gonna change things a bit. Yeah, thank you. Totally dropped the ball. that's what we end up with once the h's divide out. Okay, so now as h goes to 0, we can compute this directly. What would that give us? Yeah, negative 2x up top. The bottom, we've got x squared, and here's x plus 0 squared, so that's x squared times x squared, negative 2x over x to the 4th, and we can simplify that, so we should simplify that, negative 2 over x cubed. Yeah, sorry. Negative 2 over x cubed. So the idea with working with the definition, just like with all of these other limits, is you want to cancel this h in the denominator away, or out, because h is going to 0. You're not going to be able to compute that limit until that happens. But hopefully we've seen enough examples where you've got a feel for how these things work out. Until we start looking at shortcuts, we really don't see things outside of like polynomials, these kinds of rational functions and functions involving square roots. It's really all three that we see when it's applied to this sort of long form of finding derivatives or slopes of tangent lines. How about the derivative of the square root of x? What would be involved here? Conjugate. You have a radical involved. Conjugate's going to be involved in simplifying. So the limit as h goes to 0 on f of x plus h minus f of x all over h. Okay, f of x plus h is just the square root of x plus h minus the square root of x all over h. So let's simplify this. Multiply through top and bottom by the conjugate. Square root of x plus h plus the square root of h. Sorry, plus the square root of x. Again, initially we want to leave the denominator alone. What would the numerator be?
2x plus h.
Okay, so remember the numerator is now turns into this thing squared minus this thing squared.
X plus h minus x.
Right. So the numerator turns into x plus h minus x. All of this stuff on top is equal to that. So then we see what happens there. The x's add to 0, and then we have the h over this h, so that divides out. So then we're left computing the limit as h goes to 0 on 1 over the square root of x plus h plus the square root of x. okay with that? So as h goes to 0, what's our limit?
1 over x times 1 over root of x plus root of x.
Yeah, 1 over square root of x plus the square root of x. So we would call that 1 over 2 root x. So if you know the power rules or the derivative shortcut rules, you still have to go through this process, but you can use those as a check. I don't know that many of you would know those, but if you do, merely use them as a check. Just like if your calculator does derivatives, if the exam is about derivatives and it says find the derivative and you just say it's 1 over 2 root x without showing any work, you're going to lose credit for that. So just please be mindful if you're using the calculators that do derivatives, use those as only a checking method, because we've got to learn how to do these things by hand, unfortunately. Do y'all have any questions on that? So we'll look at a little bit of this and then I'll pass your exams back. The rest of this section deals with how do we graph the derivative if we're given the function. So this is kind of all, it's lengthy, but it's worth reading over. The graph of the derivative is simply measuring the steepness of a curve. So if you're given like a function like this thing right here, and it says graph the derivative, I think it's really beneficial to imagine, putting your pencil or your pen on this function, and at all values along this function, asking yourself, is the slope positive, is the slope negative, or is the slope of that line 0? So just like we're just tracking our pencil moving across the function. Because the writing device will give us the measure of the slope, no matter where it's at on the function. Okay, so try to envision that. We're basically looking for 4 things when we're given the graph of a function and we're asked to graph the derivative. And the 4 things we're looking for is where the slope of the function is positive. So like this line, this tangent line I draw right here, that would be a positive slope, which means the derivative is positive. The derivative is positive, then the derivative is plotted above the x-axis. So here's where f prime is positive. Where the slopes are negative, the derivative is negative below the x-axis. So f prime is negative. Where the slope is horizontal, you've got a 0 slope, which is on the x-axis. So it could be horizontal more than once, but this is when f prime is equal to 0. And where the slope of your tangent line is undefined. We haven't talked about that. It's more discussed below. But we also need to know where the slope of the tangent line is undefined, because the graph of the derivative could have a hole in it like that, or we could have the graph of the derivative with an asymptote. So if that's f prime, when we look at that graph, we can say, well, f prime is undefined here at this value, and it's undefined here at this value. So those are the 4 things we're looking at on the function in order to graph the derivative. Okay. Do y'all have any questions on that initially?